And we are live. Hi, everyone. Hey, folks. How are you doing? It's the third virtual Global Azure Bootcamp, Austria. And I'm so happy to be back. So it's one of my most favorite events in the year because I'm allowed to talk about cloud stuff. And people usually don't let me talk about cloud stuff. No, I'm just kidding. So, hey, there we go. My slides. Hi, I'm Stefan. This is my Twitter handle. It's the worst Twitter handle on the entire planet. It's Dead Parrot. If you know Monty Python, you might have heard about the Dead Parrot. And yeah, I currently work as a product architect at Dynatrace, which is a very polite way of telling me that I shouldn't write production code anymore. But seriously, it's fun. I started out working in front-end development, and as of recent, I went down the serverless rabbit hole really, really deep. And this is also why we are here today talking about Azure Functions, Rust, and serverless. Pre-pandemic, I basically organized all the conferences, meetups. No, there were a lot. But now I'm mostly focusing on Rust Linz. So if you heard about the Rust Linz meetup, it's a nice, cozy group where we try to explore the Rust programming language together. And for everybody who is in or around Linz, I heard that there might be another Technologieplauschall coming up soon. So stay tuned. This might happen. I heard some rumors. I'm not directly involved, but guess what? Meetups are alive again. How fantastic is that? Obligatory, shameless plug. I wrote a book for Smashing Magazine. It's called TypeScript in 50 Lessons. And I'm very proud of it. It's pretty beautiful. And I heard the content is also quite nice. But here, so enough about me. Let's talk about serverless. And I think I still have to ask the question, what is serverless? I need to explain the topic a little bit because this moniker serverless, this term has been beaten to death by now. So it's basically nobody knows what it does anymore. Everybody understands something different. People don't want to use it anymore. So if you follow the works of Brian LaRue, he's now trying to coin the term functional web apps or functional apps to get rid of serverless as a term and to focus more on what you're actually doing. And it makes sense that people are confused by it because serverless means a lot. There are two sides to serverless, in my opinion. And one thing is the infrastructure side, which is that you care about servers less, or the infrastructure provider has to provide less servers. So it's not server nope or server none, it's serverless. There are still servers involved, of course. But you don't have to manage them. Managing those servers is somebody else's task. And they don't have to provide as many servers as their applications. They can provide them on demand. It's auto-scaling. It's scale to zero. There's no infrastructure management on your side involved. And very important for you should be that it features consumption-based billing. So you're just paying for what you're actually using. If the infrastructure provider is allowed to turn your app off and turn it on again whenever it needs you to, then you should just pay for what you're actually using. A couple of examples that you know from other providers, Google Cloud Run, AWS Fargate, for example. As of recent, Azure has also serverless container infrastructure, which is called Container Apps, which is fantastic. So if you have a web application that is packaged in the Docker container, Docker image, you can just upload it to your Docker registry on Azure and say, yeah, well, please do auto-scaling for that. That's all I need. And it does. And you're just paying for what you need. So this is fantastic. And the other side, this is what concerns us as developers, which is functions as a service, which means I write less servers. I don't want to write servers. I just want to write the business logic, which brings you a stateless development mindset. You don't have everything available all the time. That's part of the auto-scaling nature. You know, it's stuff comes up and goes down again. So you can't say for sure that everything that you have is constantly available, which means that you need to develop for stateless applications. Your code needs to be prepared to work with stateless features. Prominent prominent examples for functions as a service are AWS Lambda and Azure Functions. Azure Functions is what we are going to talk about today. So those are the two sides, autoscaling and functions as a service. And in the best case, they go hand in hand together. So usually you're just writing what you want to write. You're just focusing on a little bit of code and deploy that, and you're happy with it. And the infrastructure provider just cares about autoscaling, just cares about getting your code scaled up so you can make sure, or you can be certain that your application runs. Important, consumption-based billing. This is what I mentioned already. In Azure Functions or in Azure in general, if you have consumption-based billing, it's usually the time your application needs to run and the memory it needs to consume. So memory is also elastic in Azure Functions, which means that you get as much memory as you need, which also means that if you free memory, then you're paying less for it. And the amount you pay is basically this area underneath. So the amount of seconds or milliseconds your application runs and the memory you consume during that time. All right, and this is also the point where we bring Rust into the mix. So I don't know if you've heard about Rust. Rust is a systems programming language which guarantees memory safety without a garbage collector. So you get C and C++ like speed since it's compiled down to machine code, but you don't have any runtime code attached to it that makes sure that memory is freed as your program continues to work. This is all done at compile time. And not only that, so this is a pretty new concept. And at Rust Links, we talk a lot about it. So you can open the official Rust YouTube and what you can do with it. And one of the biggest features is that you have this ownership system that makes sure that you are just allocating the memory that you need and that every memory is freed again once it's not used anymore, which requires you to rethink your applications a little bit. So this is usually the hardest part when learning Rust. But once you get the hang of it, it's beautiful. And the nice thing is that it's not only memory safe and fun to use, it's also a really beautiful and elegant language. So the trade system of Rust, which is their way of calling it interfaces, allows you to create abstractions that really create a high-level language which still produces highly optimized code. So this is the best of both worlds. And it's really fun. You also get features from functional programming languages, from other systems programming languages. It's elegant, it's beautiful. I love it a lot. I like to write Rust all day. But hey, think about it. It's programming language that's compiled down to machine code. It's C and C++ like speed. That's how fast it is. So it runs faster than other programming languages like C#, Java, JavaScript, Python, especially faster than Python. And also you have optimized memory management, the memory safety through the ownership and borrowing system. And this sounds like exactly those two parameters that you need to write cheap functions on Azure, because they're running faster, they consume less memory. It's a win for all of you. And yeah, we can integrate Rust with Azure Functions. It takes a little bit, but we can do it. All right, so talking about Azure Functions. Azure Functions is very similar. So let me put it different. One thing that you need to know about Azure Functions is that even if you're writing serverless, there are still servers involved. And every now and then you can feel that. They are also very HTTP heavy. So things like an HTTP trigger that triggers a function is part of the function definition. An Azure function tries to incorporate all its meta information with the function, not only the input bindings like HTTP, but also the output bindings, which means that once you have a result, you can either put it out on HTTP again, or you trigger another service. We're going to see some of that during the examples. And and it builds up on the Azure Web Jobs service that is in Azure around since forever. One thing that is different to other functions as a service providers is that the unit of deployment is not a single function, but a function app, which means you have a couple of functions bundled together and they scale out together, they are deployed together. You can think of writing, for example, a Node.js server, but not writing the server itself, just the hooks for all those routes. You're just writing that, and everything else is done by Azure Functions itself. But also the scale unit is the same. You can think of deploying several Node.js servers and putting up several Node.js servers. And what you need to get it done is Azure Storage to store function apps or to store logs, etc., some other meta info. So those are the basic requirements. If we talk about the execution lifecycle, so usually, this is important. This is the whole auto-scaling part. And usually, Azure Functions has a scale controller that monitors events. And depending on how many events that you have, it tries to find an unspecialized Azure Functions server that is blank, that has no workloads running. If the number of events is handleable, it points you to your already existing or already running Azure Function servers. But let's say you don't have any running, or let's say you need more, then it tries to find an unspecialized server. Then it specializes it, which means it mounts files to your server, it applies some application settings, then it boots up the function host, it resets the function runtime, which executes the functions, it loads the meta information from the function JSON files, this mounts your functions to some API endpoints, extensions are loaded if they are here, and once the functions are loaded into memory, they are being executed. So this is the usual boot up scenario. And all the pink parts on this chart happen during so-called cold start, which means this is the specialization phase. This is where Azure allocates a server for your application. Once it's running, you are just looking if there's another event and web execute code because everything is running already. And as you can see from all the pink boxes, cold starts on Azure can be slow. They can be slow. So we are talking here, I don't know, depending on the technology that you use, a couple of seconds. With Rust, we're going to see that this can be much, much faster. This is also one of the reasons why you should consider Rust in the first place for Azure Functions. So now your application runs, your functions run. What happens if there is a trigger, for example, an HTTP trigger where I say, well, I want to execute this API backend. The trigger is coming through an input binding to the Azure Functions host. And depending on your technology choice, 3 different things can happen. The first thing and the most easiest thing is that if you have written a C# or F# function, you compile it down to a DLL. Since the Azure Function host is built up on Azure Web Jobs, it can load this DLL in process, can execute this function in process, returns the result and distributes it to all the different output bindings. Excuse me. So this is the easiest part. If you've chosen one of the supported languages of Azure Functions like Python and Node, and there was Java, I don't think there is anymore, if I'm not mistaken, but there was Java. Java was supported as well at one point in time. Then you are getting a function runtime provided by Azure that runs out of process. So this is then a little Node.js server, a little Python server that works by convention to load your functions and boots up your functions and talks via gRPC with the function host. So the function host sets off a gRPC call to your Python server, to your JavaScript server, and the response is being also sent via gRPC. And those are the things you don't have to care about. So you're just writing the functions, either in C#, F#, Node, Python, whatever, and everything that needs to do the management to talk between function host and your app, that's handled by the runtimes provided, either in process or out of process. So far, so good. But we want to write Rust, and Rust is not a supported language for Azure Functions, at least not yet. There's so much going on with Microsoft and Rust that I could expect that to happen pretty soon. But they have some really nice documentation on for that. But Azure Functions has a possibility to allow for custom handlers. custom handlers like a web server written in Go, a Rust server. And we're talking servers here again. So you write a custom handler, which is just a random web server, and you talk via HTTP to the function host. So yeah, I'm sorry, it's not the serverless part where you are not writing servers, you write servers, but at least you don't have to care about scaling servers. And you can integrate your mission critical code into an auto-scaling infrastructure and let it talk to a lot of other different Azure services. And before I'm going to show more slides, I'd like to drop the slides and I'd like to share my Visual Studio Code setup because, hey, let's do some real examples. Let's see how this works. So, dear Regie, thank you very much. I'm going to stop sharing. I'm going to re-share again, and you should be able to see Visual Studio Code. Is that correct? And so no, I guess you are seeing Visual Studio Code, but I don't. There it is. Okay, and you should see a blank Visual Studio Code. Is this also correct? Okay, cool. Yeah, looks good. Fantastic. Let's go. Alrighty, what you see here is a pretty boring empty Visual Studio Code. Let's fill it with content. Let's make sure that we're getting something out of it. I'm hopefully logged in Azure. The first thing that I do is that, hey, I'm in this folder, GAB, that's short for Global Azure Bootcamp, and I try to create a new function app. So this should work, func new. All right, fantastic. Those are the supported runtimes. I forgot PowerShell. So little scripting in PowerShell is a totally valid and wonderful use case for Azure Functions. But I don't want to write .NET. I don't want to write Node, Python. That's not what I'm here for. I want to write Rust. So I select custom. I want to have a custom runtime. It creates all those necessary meta files. We are going to work with them in just a second. And to start everything, I want to create an HTTP trigger. That's okay. I want to create an HTTP trigger. I want just to set off a little API call that maybe triggers sending an email or something. All right. And the function name, I call it contact. There you go. All right. So now Azure Functions is set up. I have a host JSON, which is the information to instantiate the function host. I have a couple of local settings if I want to develop locally, where I can have a Azure Web Storage server, blah, blah, things like that. I have a little test script. I'm going to show that later. And here's the file, the folder that contains all the information for my contact function. Function JSON, I set the auth level to anonymous. This makes debugging a little bit easier, which means that I can just call it and it's okay and don't worry about it. All right, anonymous HTTP trigger, HTTP in and get and post, and I have an HTTP out. So those are the input bindings and output bindings, which means here I can trigger something via HTTP and I get this request in, and I expect a result that's also going out via HTTP. And I name it HTTP response, just for now, because I need that later. Alrighty, so Azure Functions is set up. It does nothing, but it's set up. What I want to do now is next to this Azure Functions project, I want to create a Rust project. And I do this by taking cargo, which is Rust's package manager, and I say, wait, please initialize this folder as a Rust app and call it handler. This is just because I'm lazy. I'm going to wire up a handler binary. And if the name is the same as the binary, then I don't have to rewrite stuff so much. So I just call it handler. There you go. And Rust is initialized. What I get is a cargo toml file where I can install dependencies, and I'm doing that already. So I copy a couple of dependencies from my nodes over here, and I have here Exam, which is a little web server. I have Serdi, which is short for serializing, and deserializing, which is the best thing since sliced bread. It allows you to map JSON files or YAML files or XML files over to some Rust structs, just like that. You don't have to do anything. It's beautiful. So I'm going to install that as well. And I'm installing Tokyo as an asynchronous runtime. Async in Rust is a huge topic. I have slides on my website that can entertain you for hours if you are curious about that, or you just shoot me a tweet or hang out with me. I'm happy to talk about Tokyo a lot. Alrighty, so let's save this. There's a couple of dependencies, and it looks good. Alrighty. So what I also get is here this source folder, and this is a hello world in Rust, and I want to fill that with real world content. I want to fill that with my little web server that I'm going to connect to to Azure Functions, so I can write Azure Functions in Rust. What you see here is that I already produced the target folder. This is my tooling, Rust Analyzer. It's already fetching all the meta information in the background, so I can get fantastic autocomplete. Okay. Dependencies are set up. First thing that I do, I'm going to delete my main function and create an asynchronous main function. So don't worry what that does. It's a macro that tells the asynchronous runtime to initialize itself and to take this as its main handler. That's all I need. Then I'm creating a new XM app. So I create an app. I say, please create a new router. And as you can see, so Rust Analyzer tells me, well, do you mean the XM router? I press enter, it gets imported. So it's in my imports right now, and I can just use it. So I can create a new router, and I add another route, and I call it /API/contact. Don't worry about the last thing for now. So there's a second argument that I need. And this is important. So if I'm creating a web server, I need to follow the same URL pattern as Azure Functions does. So every function that's being created, like this contact function here, is being mounted at /API/contact. If I have an API function that's called list, it's mounted as /API/list. And if I'm creating a web server here, this string needs to be the same route as the one seen by Azure Functions. So route the new route API contact to map this call to contact to this particular route. Alrighty. What I also need is the actual function. So I'm creating a small function contact. I'm going to fill it with live later on. Async function contact. There you go. And I say, well, I want to enable post requests. Again, importing it to contact. There you go. This is my router setup. That's all I need. Rust Analyzer says I need to have type annotations, not now. Rust is really good at inferring types, but since I'm not using the router anywhere or the app anywhere, it can't infer the types it needs. Don't worry, we're getting there. Then I need to map my newly created app that forwards all /API contacts to this function contact. I need to map this so I need to put up a server and need to listen this server to the functions port. So Azure provides me with the functions port. This is a different one with each startup, so it's being assigned dynamically, which means it's stored in an environment variable. And the environment variable is called functions custom handler port. There we go. I want to extract this from my environment variables. So I say, well, this port, I can reassign this variable. I can shadow it so it becomes a different one, which means naming things gets a lot easier because I can reuse names if they just change type, which is fantastic. Where I say, okay, from the environment, get this variable, which is the port key. I say, well, sorry, there's a thing. Unwrap this, which means this might result in an error. If there's an error, which means the variable is not set, then please just use the string 3000. And I'm using a string here because environment variables are strings. And then I want to parse it to an actual number. And I know that this works because I can pass 3000, so I'm going to unwrap this as well. This doesn't look so bad. I'm missing an equal sign here. Alrighty. And I'm calling cargo format to have it nicely formatted. That's also not too bad. Okay, so port is set. What I do now is I take another address, which is a socket address from, and I'm taking here a tuple. I'm going to let it listen to localhost on port. There you go. And let's say the XM server bind it to this address, serve my app. It's not important what into make server it does. Gotta wait because it's asynchronous and unwrap, so let it die if it doesn't work. There you go. The error is away because now it knows what to map the router to, because I've used it down there, which is quite nice. And this is all the server setup that I need. So if you have the right frameworks, you know, it's a very low level language, but if you have the right frameworks, it's easy as that. So I want to set up HTTP calls. I have a little HTTP test file here. This is done through the REST API extension in Visual Studio Code, which is fantastic because I can write requests just as plain text and I can send it over to a server now. And I want to post to /API contact this little payload, like, hey, a name from the Global Azure Bootcamp, a message, a mail. And for that, I'm going to create a little struct. Contact. I'm going to import this deserialize trait, which means that I can now make sure that if I have a JSON output that has the similar structure, I can create a struct out of it. This is pretty nice. And I say in this contact function, so this is the actual function that I'm now implementing. Please get some payload that comes via JSON, which is of the structure of contact. So this is how I'm getting from here, from this little JSON input to an actual struct that I can use, which means now I can print line. Let's print line all those fields so we know that it's working. Payload.name, payload.mail, and payload. What's the last one? Message. There you go. And I need to import JSON, of course. So there you go. Good. And I just want to say, well, this worked. Send the status code OK, and send some JSON output. I also say status 200, something like that, just for demo purposes. So. And it's also, no, it's not a tuple, that's okay. I need to tell Rust that I'm going to return a response. Nope, it's not okay. I might have a bug. Ah, okay, the quotes, that's okay. Now it works. Alrighty, that's my little server. Let's build it. Takes a little while. It fetches all the dependencies. Let's run it. And now I can test my server like this. It's listening on localhost 4000 /API/contact, send request. There you go. It works. It's not the prettiest JSON. Maybe I need to rework that, but I'm getting everything from the input, and I'm having a proper output. This is what I'm supposed to get. But hey, that's just my web server. This is nothing to do with Azure Functions yet. But you know what? That's not actually that bad. If you have a web server already running, in no matter which language you're writing it, you can auto-scale it with Azure Functions just like that. When you listen to the functions port, to the functions custom handler port. So this works. This is fantastic. Now I need to change a couple of things in the host JSON. So I have a custom handler and I say, please, the executable path is handler. So this is just the binary that I'm creating. If you're on Windows, it's handler.exe. And what I'm also saying is that I want you to behave like a proxy, like an HTTP proxy, which means I say enable forwarding HTTP requests to true. And all the HTTP requests that hit the function host are just being forwarded to my little server. And that's about it. Okay, I'm killing my server now. I'm copying cargo build -- release. I want to have a release build, which is much faster. It's much optimized than the debug build. And I want to deploy that. Takes a little bit of compile time. This is probably one of the downsides of Rust, that compile times can take quite long. But there you go. Then I'm copying handler to here, because this is where I say the default executable path is located, and the same func start. So I'm starting the Azure Functions host. Oops, it's running in another tab. I'm well prepared, as you can see, because it's running already somewhere. Let's start it again. Yeah, okay, now it works. So it boots up the Azure Functions host, and now it maps the custom handler, and based on the folders here, it creates all those routes. For get and post, this is part of the function JSON. Fantastic. If I'm going to my HTTP file and I have here the same payload, the same request, but now I'm going to localhost 77.1, I'm trying to send the request over Azure Functions. So let's go send request, and it works just as well. So as you can see, the server is now a different one. It's the server that comes from Azure Functions. But hey, look at that. It works as intended. It just have wrapped it in the whole Azure Functions auto-scaling nature. All right, and now comes the difficult part. Now I want to deploy it live and want to make sure that it also works live, which means I need to create a Linux binary. And this is so if you're doing Rust, if you ever done cross compilation for Linux from a Mac or from a Windows server, this can get nasty. This can involve some really weird linking errors or tools that you need to install that you don't want to install. I have one tip for you. Use SIG-build. So SIG is another systems programming language that's pretty new, and it's also very interesting. But the best thing that comes out of SIG is SIG-build, which allows you to build cross-platform targeted on Linux from any system that you're on. No matter if you are developing on Windows or if you're developing on Mac, like I do, with SIG-build, you can compile, let's say, for unknown Linux MUTL. So I'm creating a release build for Linux for the MUTL bindings. This will also take a while. Again, we're compiling here, but I guess it's even faster than my Mac build, which is quite interesting. So the Mac build took 15 seconds. Let's see how long this takes. And there you go. Okay, it's also taking a long time, maybe longer. Do we have still time for that? There you go, 19 seconds. Oh, I'm sorry. This is just the first one. You know, it needed to compile all the dependencies first. The moment I'm doing an update, this build is much, much faster. I'm again copying this one thing over here. I'm also creating a func-ignore file where I say, please, if you deploy the whole thing, please don't deploy my target folder. There's lots of meta information there that you don't need. Okay, and now I'm creating a new function app. I'm using the extension now, the Visual Studio Code extension for Azure Functions. I already have a couple of here, and here I have my local project. And let's say, please deploy those. I'm creating a new function app in Azure. I call it a Rust GAB contact function. Rust GAB. I'm selecting a runtime stack. It's custom handler. A location, let's go to North Europe. That's okay. And let's see if it works. It's creating the app service plan. So lots of stuff is happening here. Creating a storage account. Yeah, you know, there's lots of stuff involved. I'm very happy that the Visual Studio Code tools are doing that for me. And I'm using here Visual Studio Code because I never can remember all the command line tasks that I need to execute. So this tool is quite nice. Okay. It creates the new function app. That's the last part, and then it should be here available. Those are some other tests. Those are the tests from last time. So if this doesn't work, I still have the one from last time, hopefully. Still creating. And where are you? So there you go. Now it's deploying. Check the output window for status. This is going to be interesting. It created the application. And so the zip package size is just 650 kilobyte. That's not that much. Deployment is successful. And So anyway, I'm going to try it out now with the one that I already had. It's the same app. Oh no, it's not the same app. I guess I changed something. Never mind, it's here. So let's copy this URL. Rust gap fn, copy it to here, Rust gap fn, and send the request online. Waiting. Maybe I did something wrong. Hopefully not. Okay, no, this takes too long. I'm sorry. I screwed something up. Let's try it again with the old one. Let's cancel this. Send a request. Waiting. Okay, I have an internal server error. Also with, which one is that now? Yeah, okay, I broke something. I guess I broke something. But let's try Rust gap fn again. Rust gap fn, send the request, and this doesn't work. So let's remove the handler. Let's create. Oh, this happens all the time. I'm super sorry. I need, of course, go to the Linux build. I deployed the Mac build. How anticlimactic. And now I'm going to deploy the whole thing again. And while so this deployment should be a lot faster now. Deploy. And while I'm doing that, I want to show you a couple of other things. So this is great. Once it works, once I'm going to show you that this actually works. We are able to hook up any HTTP server to Azure Function, and we can run it, and it's fast and fantastic. But that's just half of the story. Usually when you're writing Azure Function, you not only want to execute HTTP servers, but you also want to integrate it with other services from Azure. So you want to have an output that maybe not only goes to HTTP again, but also sending an email or a SendGrid or queuing something on some RabbitMQ or whatnot, or deploying something into CosmoDB. So this is what Azure Functions is actually there, that you can have this little glue code in between where you glue everything together and create a couple of output bindings that work together. So this is what you actually want to have. Right, let's try this again. I hope this works now. And send request. Waiting. Okay, maybe I screwed something up again. Never mind. Let's go to the next example. Okay, and I want to do that as well. And I want to have the possibility to hook up different things. And to do that, where are we? I need to turn off forwarding HTTP requests. And this is now something interesting. If I turn that off, suddenly I'm in charge of doing all the work those Azure built-in runtimes do by themselves. So I don't have this contact form here anymore. What I'm getting is, let's say I'm getting a request that is of type request body. There you go. And let's see what this request has in store for us, req.body. And what I also need to do, rec.body, there you go. What I also need to do is I need to send something different here. I need to send some actual output that works just like the Azure Functions outputs. I prepared a couple of structs for that, that nest, serialize, that nest the whole thing. Import serialized, that's great. And I'm having an output that looks kind of like that. So I'm defining all my outputs. I'm defining the HTTP response, which has a body and a status. So this is the HTTP response, and this is the actual content then that's being mapped to HTTP. So let's not look at the request body for now, but this is now the setup that I need to open it up for more outputs. As said, I need to do a lot more myself. I'm building it, cargo build release. Let's get rid of all the unused imports. And if I run it in release mode, And going over to my tests again. Yeah, so if I'm sending this request now, nope. What I also need to do is I need to get rid of /API. So it's not forwarding anymore. This API stuff is now part of Azure Functions of the host, and the mapping is different. Alrighty, cargo run release, which means now my HTTP test here, that should work. Cool, this is the output that I get from the server. Now I'm going to start my function host again. Fail to start a worker channel. Oh, this doesn't work. Of course, I need to copy it again. Target, release, handler, there you go. Now I'm starting it again. Now it works fantastic. If I now send the same thing over to the host with 7071, you can see /contact. No, it's /API contact again. This is the binding from Azure Functions, forwarding it to contact binding from me. I'm sending the request. There you go. And it sends a whole lot of thing. And what I'm getting back is the status code that I'm sending, 200, and I'm setting mail sent. This is the body that I'm getting here. There you go. This is this particular body here. Alrighty. So this is how I'm opening up Azure Functions for more than just one output binding. Let's see what I'm getting in. Let some body. I'm going to create a string representation of this body. So I want to see what's the actual input. Let's build it again. And let's copy it again. I should have automated that. There you go. Func start. And now if I'm going to call test HTTP, I see that's just body streaming. That's funny. Let's go to the entire request. Let's build that one. Let's see what we're having here. Build, release. Remove the old handler. I'm just doing that because this cranked me up when I worked with it yesterday. I'm starting this whole thing and I'm sending the request here. So yeah, this is the whole stuff that you get from Azure Functions. That the method post, URI contact version. Those are all the headers. This is all the meta information that you would need to parse the user agent. This is the functions host in version 4. And somebody in there is the actual body that you can access. And you would have to unwrap this body and make sure that this is mapped to the right struct. So there's a lot more meta information that you need to handle. But yeah, so this is the setup, and now you can start wiring up SendQuery. Now you can start wiring up a message queue. This all works. Alrighty, I promised you before we end some insights on what it means to use Azure Functions. Actually, I'm going to stop my screen again, and I'm going to reshare my screen again to my slides. You should be able to see my slides again. Okay, so we did a couple of tests. And one thing that we did is a palindrome products test, where you're creating, where you're taking a tuple of numbers like 10 to 99, and you multiplying each and every combination with it. And then you're looking in this set of combinations for numbers that are able to be read from the front to the back and from the back to the front the same. Like 101 is a palindrome number. 9009 is a palindrome number. You get the idea. So I'm creating those tuples. I'm doing the combinations. I'm creating a product and I'm looking for those palindrome products. And the nice thing is, this is stuff where, for example, JavaScript is really bad at, because number crunching is not JavaScript's strength. So let's look at some times there. Usually, and that's interesting, if you have a cold start time for Node.js backed Azure Functions, you take around 700 milliseconds, which is already quite fast. Don't get me wrong. This is much, much better than 3 years ago when I presented Azure Functions for the first time, where we were in the minutes. So 700 milliseconds is really good. And then you have a powerhouse actually, so this is nice. If you do a rerun from a hot Node server, then it takes a millisecond for hello world. In Rust, and this is fantastic, it takes less than 100 milliseconds to boot up a Rust server. So usually it settles around 50 to 60 milliseconds to boot up Rust on Azure Functions. And the reruns are less than a millisecond. They are basically instant. If it works, I suddenly, sadly, my binary didn't deploy right. But hey, I'm going to change that later on, and you're getting some notes on that. If I'm calculating the first palindrome products from 10 to 99, Azure Functions on Node needs 9 milliseconds, less than 5 milliseconds on Rust. If I go from 100 to 999, Azure Functions on Node needs 80 milliseconds to calculate that roundabout, and on Rust it takes less than 15 milliseconds. And if I have 1000 to 9999, which is huge, which takes a while, it takes 10 seconds to calculate on Node on a hot Azure function, and less than a second on Rust. So this is how fast you get. Usually JavaScript is fast, but usually you get a 10x performance if you're switching to Rust. So if you have anything that is critical, that needs to be fast, anything where you do heavy computations, using Rust for Azure Functions is really, really good. Benefits that you get, you have significantly lower cold starts, and it's just a server, which means you can migrate your Rust apps or any app that runs on HTTP right away to Azure Functions and work with it. So the migration is pretty easy. And the cold starts depend usually on the size of the function app. If you have a JavaScript app, you need to bind every function on its own. This takes time. You need to mount every function on its own. So usually they tell you if you have more than 10 functions, consider creating another app for that. This is less of a problem in Rust because you have a binary that's 1 megabyte and you boot up the binary and that's good. So the moment you boot the host, everything is there. No need to do anything extra. And again, it's super fun. Alrighty, so this is it so far. I guess I'm in time looking at the regie if I'm still in time. I think so. A couple of notes to end the whole thing. I have a couple of materials. So there's lots of stuff on understanding cold start, lots of stuff on getting started with custom handlers. And here, this is, I guess, the most important one. This is my blog where you find all the slides, all the examples, everything to try out Azure Functions for you today. So there's lots of material already up there, and everything that I've shown you today is going to be up there as well. And yeah, so if you want to learn Rust, stop by at Rust Linz. It's fun. It's a fantastic community. We are very open to beginners. We welcome you to try it out with us together. There are a couple of companies in Linz already who are going to use Rust and who are using Rust in production. So this is a language that has a future, and I think it's a great partner for Azure Functions. And I want to thank you for having me. And I'm going to be in the Q&A later on. Alrighty. Bye-bye.